Okay, all right. Can people hear me okay? Great, thanks, I'm seeing a few hands. So my name's Matt Campagna. I'm a member of the AWS crypto organization or cryptography organization. They have a few commercially facing services, namely the key management service, Cloud HSM, the AWS certificate manager and private CA, as well as the secrets manager. And on that team, I run a small group of cryptographers and software developer engineers. And they have a few primary focuses that are often AWS-wide. I think if you heard Steve Schmidt's keynote speaker when he was talking about the 1,800 new services or features that they have to do an AppSec review, if any of those require sort of a new development in terms of using cryptography to provide the security services, then that goes through our team and we do the design and analysis review for that. So things from AWS key management service itself to how we encrypt objects on S3 to doing basic things like link encryption, how are we engineering those solutions. In addition, we have an eye on keeping discussions open with our customers to understand what are the other security services or threats that they're facing that are concerns to them that we're not providing today, as well as participating in the international community of cryptographic research and standardization. And this talk sort of reaches across all three, how we sort of approach the classical way we approach providing cryptographic security today, some of the threats that we see and our customers see to that classical approach that has sort of had the international community is responding with the generation of these quantum safe or post-quantum cryptographic schemes. These are still a few years away from being sort of fully standardized schemes that we're going to want to deploy, but we know that they're going to cause us to have to change our applications and protocols to accommodate for them. So we're doing that early with something called hybrid key exchange, and we've defined how to do hybrid key exchange within TLS. And then we've embedded that into our open source library for TLS signal to noise. And so at the end, we'll have a post-quantum version of S2N that not only we can start understanding how our applications and protocols are going to have to change, but so can our customers. So it's available today to be downloaded from AWS Labs in GitHub. So I'll just start going through sort of our approach to classical cryptography. Typically, whenever we design a new security application or protocol, we're really looking to cryptography to provide some key security services. In particular, data integrity, the property that the information hasn't been modified by an unauthorized user. And we rely on cryptographic functions such as hash functions, namely SHA-2 and SHA-3 today, as well as some other techniques borrowed from authentication and non-repudiation. Oops. For confidentiality is the property that the information remains secret from unauthorized entities, so there's no disclosure of information. And to provide that, we apply an encryption scheme like AES is probably the most well-known, and one of the modes of operations like GCM. But then we also use key agreement schemes like Diffie-Hellman or elliptic curve Diffie-Hellman to establish a key to encrypt that if we're doing sort of network traffic or session encryption. Next, authenticity. And here, we're really talking about two different types of authenticity, both entity authenticity, how do we know the entity that we're speaking to is the one we intend to speak to, and message authenticity, sort of how do we know that the message as it came from somebody hasn't been altered from that author, so to speak. And for that, we use message authentication codes like HMAC or codebook-based schemes like GMAC and CMAC. And finally, we have non-repudiation, which is the ability to hold people accountable to their commitments. And the security functions that we primarily use there are signature schemes like RSA and ECDSA. We're always selecting the scheme that most fits the application in providing these security services. And a few things go into selecting that scheme. One prominent one is the security. And the security of a cryptographic algorithm, there are sort of two aspects here. there's this one very quantifiable aspect of what's the computational complexity of the best known attack. And this is a nice number that allows us to compute sort of an equivalence between different types of algorithms to get some way to measure how they are, how secure they are relative to each other. And that helps us define the security lifetime, not just of the algorithm, but also the data that it protects. And then there's the harder part of this is, what do we mean by best known attack? And how much assurance do I have that there isn't another attack that we don't know about? And for that, that's not quite as quantifiable. It's really looking at how long has the fundamental problem or algorithm been studied, and who's studied it, and what is the quality of that publication record. It's very difficult to sort of measure that, and unfortunately there's no sort of compression for the iterative process of analyze, discover, and disseminate that's building one person's research upon another's to really get a high assurance cryptographic scheme. So if we look at the technology that we're using today, on the left-hand side I have sort of the common cryptographic technique or technology we're using today: elliptic curve cryptography, finite field cryptography like El-Gamal or finite field Diffie-Hellman, integer factorization technology like RSA, the codebook schemes, AES and DES, the SHA family of hash functions, and a relatively new scheme, Cha-Cha-20, that we're seeing sort of recently been starting to be widely adopted in the industry. And we can see it takes some time to go from invention to standardization to widely used, or even discovering what the best known attack is. So if you look at just finite field cryptography, it's certainly maybe one of the oldest, but it's not really an anomaly in terms of the time it takes to go from invention to best known attack to widely deployed. And that takes 10 to 15 years. So it does take a while to say we need a new asymmetric cryptographic scheme. And finally, on the right-hand side, I have some mathematical formulas based on essentially the key size that allows me to equate sort of the computational complexity of the best known attack. So this table sort of re-rasters all that information and says, well, if I just want to compare these schemes in terms of cryptographic strength in terms of bits on the left-hand side. So 128 bits means it takes on the order of 2 to the 128 amount of work to sort of against the best known attack against those schemes. So I will say we're no longer engineering at the 80-bit security level, and hopefully no one else is. I think if you think about 80-bit security today, Bitcoin does 2 to the 70 work every 10 minutes to advance the blockchain. So if you look at 2 to the 10 blocks of 10 minutes, you're looking at roughly 7 days before somebody could, not just theoretically, but actually physically, computationally break sort of a SHA-1 security level, at least for pre-image resistance. And what I have in bold here are sort of the security level that we're engineering, sort of what our targets are when we're producing a new product or services on trying to hit AES 256 for encryption, SHA-304 for hashing and data integrity, elliptic curves on a 384-bit curve, and finally RSA and Diffie-Hellman on 3072. So then how much confidence do I have that that's the security level I'm going to be to maintain in the future? And there I have to go to the publication record. And I would take this very much with a grain of salt, because it's very difficult to say I've looked at 200, 300,000 papers and said they all equally apply in terms of quality. So there's no really quality metric associated with this. This is just a count of the papers. I went into Google Scholar, put in some keyword searches for the number of, and just looked at the paper count. And I did some sort of tuning of these to make sure, and I looked through the first couple, I spot checked up to about 2,000 up to about 2,000 in each queue, maybe every couple of hundred. I would look at a few papers and their title and abstracts to make sure they didn't sort of wander into some other use of the same three-letter acronym. So they've been tuned a little bit, but you can see, our expectation of our most secure algorithms kind of bubble up to the top, and the relatively newer ones that might have less academic support for are down towards the bottom. And we use that to sort of define what is the security lifetime of the confidentiality requirement. And that's going to depend on the data that you're using. So if you're looking at sort of temporary security credentials, those are designed to only be usable for a few hours, maybe a day or so, and then they're no longer of use. Similarly, earnings report, kind of by the end of the quarter, we make information public, or companies make that public. And looking at where are we engineering today, we're engineering on behalf of our customers based on sort of corporate trade secrets, classified information. This is going out multiple decades. And really, we'd go further if we really believed we could accurately see or forecast technology 20 or 30 years in the future. I think the track record of trying to forecast there is not so good. And I don't think we'd be significantly better. So here's one of the things that keeps me up, and I don't think I'm alone here. I think we've certainly heard from other people that this sort of a common sort of concern of the security engineer. But for us, it's very impactful. In particular, all our customers and all our customers' customers are primarily communicating with us over a public network like the internet. And they're using some asymmetric key agreement scheme to provide confidentiality to that data. So whether that's IPsec, SSH, or TLS, it's all going over some public network. And that public network is outside of the control of us, and it's outside of the control, often, of our customers. And so an adversary could selectively record portions of that data. And at some point in the future, some new capability might arise, and that will allow them to somehow compromise not just the existing communication, but any data that they've sort of recorded in the past, they would now be able to harvest and use the plain text for. So this is sort of the motivating thing that sort of keeps me up, makes me come to work. And one of the new capabilities that is certainly roughly on the horizon, to some horizon, is quantum computing. So quantum computing is different than classical computing today. When we think of computing, we have a classical memory is stored in a bit. That bit can hold either a 0 or a 1. By contrast, a quantum computer uses something called a qubit. And a qubit in superposition can hold both the values 0 and 1 at the same time. What that means is sort of comparing, if you have n classical bits, you can hold one of 2 to the n possible values in that register. However, if you have n quantum bits or qubits, you can hold all 2 to the n possible values at once. And this allows you to construct algorithms that can be computed on all 2 to the n inputs at the same time. And there's a bit of a trick here that I can't confess to really know extremely well, but only some algorithms are amenable to sort of getting the right output. But we do know 2 of them, and they tend to be, in theory, devastating to some of the classical cryptography that we use today. The first is Shor's algorithm, which can solve the discrete log problem as well as integer factorization. And the result of that is it breaks the Diffie-Hellman schemes, it breaks the elliptic curve cryptographic schemes that we're using, as well as RSA. So these are schemes that we commonly rely on to provide confidentiality over that channel. And then there's Grover's algorithm, which is an algorithm that allows you to search through an unsorted list in the square root of the length of that list. And this has an effect on just sort of searching for, exhausting over a key space for a symmetric cipher, or finding a pre-image to a hash function, to a square root. So now we can revisit the common technology that we're using today against these new sort of albeit theoretical attacks, and we get a different picture. We have now, for elliptic curve cryptography, finite field cryptography, and RSA, we have Shor's algorithm, which is polynomial in the logarithmic size of the key that we're talking about, which effectively just breaks those systems. And then for AES SHA, for the classical symmetric key encryption schemes, we have basically a square root in the security level, which isn't devastating in the same way, because if we still need 128 bits of security, we can move to AES 256, and that'll still provide us 128 bits of security. Okay, so with quantum computing, the current state is that if somebody has a large-scale fault-tolerant quantum computer, the impact can be that the confidentiality of all these TLS and SSL sessions, TLS, SSH, and IPsec, could be discoverable in the future. There's also the risk that anything that we sign today could be forged in the future. The risk here is not quite the same. Like, authenticity tends to happen in the moment. Like when you're doing a TLS connection, you can't go back in time and trick me into communicating with you that I was communicating with somebody else. Either the technology existed at that time or not. Unlike confidentiality, that sort of has a lasting requirement that it stays secure. So fortunately, there's no large-scale quantum computer today. There's steady progress. But so far, it's been, I would say, relatively slow progress to a fault-tolerant quantum computer. At the same time, some of the algorithmic work has been reducing the number of qubits required. To do something like factoring RSA 2048 would take a quantum computer with roughly tens of millions. I think the last paper I saw required 18 million qubits to be able to factor RSA. And to give you an idea of where the industry is at now, is they're roughly at 50 qubits. They're just on the horizon of being able to do 50 qubit computations. So it's a considerable ways away. But there are two things that are happening here. I think out of Google Labs, there's this Nevin's law that's basically saying, looking at the advancements that they've made, and saying that it's doubly exponential. So unlike Moore's law, where you're going 2 to the x every 18 months, increasing that exponent, for doubly exponential means it's 2 to the 2 to the x. So that they're conjecturing that this slope could be quite steep to get to a large-scale quantum computer. And at the same time, we're reducing the requirement on the number of qubits to do any of these operations. I will say, I don't think, this is sort of a conjecture that I have maybe, but I don't think quantum computing is going to really replace the commodity computing, the wide-scale commodity computing people are doing on EC2. They'll probably initially operate sort of like as a secure coprocessor to do special computations for you. But we can look at the timeline for quantum computing and sort of look at least into the past and conjecture into the future. So going back to sort of 1981, where Richard Feynman first sort of suggested we could do quantum computing or computing using quantum mechanics. And then moving into the 90s, we see the algorithms first beginning to be really developed and studied and analyzed. And a great example of the iterative process is Simon's algorithm, which solved the hidden subgroup problem using a quantum computer, which was really the genesis of what Shor used to do Shor's algorithm that delivered the break to integer factorization and the discrete log problem, followed by Grover's algorithm. And then we went through a period of early research and development of actually building quantum computers, starting with qubits to prove some of the basic properties, 2-qubit computers. And we're at the verge now that we think, this year sometime, we expect to see 50-qubit operations being done quite, without too many errors. And with a few years after that, 100-qubit computations. And this sort of brings up that term you may have heard called quantum supremacy. It's this tipping point where it's no longer feasible to sort of simulate quantum computing with classical machines. Today, as I mentioned, 2 to the 80 is probably within reach for certain special hardware networks. 2 to the 100 is quite a bit farther outside of the reach of what we could muster, even if you map out Moore's law for that time in the future. And if you look at when will we get to a quantum computer of the size to factor RSA 2048, well, I have a big guess circle, which says I don't really know. Some people put that chance. In particular, there's Michele Mosca, who was one of the founders of the Institute for Quantum Computing at University of Waterloo, and he puts that number at maybe 1 in 6, 1 in 7 by 2026. So there's certainly some probability that such a machine could exist. It's not clear one will ever exist in my mind, but it's a risk that we have to sort of examine, and so has the international community, which has given rise to this post-quantum cryptography or quantum-safe cryptography. So when people talk about post-quantum cryptography, for the most part, they're talking about developing new cryptographic algorithms that run on the classical computing 0 and 1 bit registers that we use today, that are designed to be secure against a quantum adversary should they ever occur. And in particular, the community is focused on key establishment schemes and digital signature schemes. And we do know that it takes a long time. We've seen by just looking how long it takes to go from an invention to a standard to a widely deployed with robust implementations takes 10 to 15 years. And so the notion is we should start now, or we should have started a little while ago, so that we're outside of any risk to the security of our information today. So one institute, there's the National Institute for Standards and Technology. It's a US government-based organization, and they've started a standardization process. And I'd say it was really kicked off in 2015 when NSA made changes to their Suite B algorithms. It basically said, if you haven't migrated from finite field and RSA to elliptic curve, maybe wait, because we're going to be putting out new requirements for quantum safe or post-quantum cryptographic schemes in the next 5 to 10 years. And if you have moved to ECC, then move to the higher security level, the 384-bit curves. That was followed by NIST sort of indicating that they were going to do a call for proposals to start their NIST standardization process for post-quantum crypto. In 2017, the first round of candidates were submitted. There were 69 complete packages, included 49 public key encryption or key encapsulation mechanisms and 20 signature schemes. At the beginning of this year, in January, they announced round 2, sort of a culling of those initial submissions, and that's now 17 key encapsulation mechanisms and 9 signature schemes. Later in this year, they'll hold their second conference. That'll be at UCSB, University of Santa Barbara, all the second round candidates will sort of present the current status of their designs. And that'll be followed by more analysis, perhaps a third round. NIST hasn't committed to whether they're going to do a third round or not, or they might just move right to draft standards on a few of these schemes. And you can see their timeline, even though it's maybe 6 years, 5 to 6 years to get to draft standards, it's still aggressive. And there are a few organizations that can really harness the cryptographic community to focus on the set of algorithms that are really required to go from sort of conceptual to something that's worth standardizing in terms of we all agree that this is secure. AWS has also been participating both in the research and development in this space as well as standardization. We were involved in setting up the ETSI, which is the European Telecommunications Standards Institute, and the Institute for Quantum Computer computing quantum safe cryptography workshop. And this was really to sort of begin to spur the community, basically targeting people from various government organizations, the research community and academia and corporations to sort of alert them that, we really need to start now. And a result of that was the ETSI industry specification group for quantum safe crypto that we've been participating in. That became a technical committee, which is sort of ETSI parlance, from being able to sort of make rough recommendations to issuing standards. ETSI is one of 3 international standards organizations that their standards can be mandated in the EU for EU compliance. In 2018, we began participating with the Open Quantum Safe Development Team. In 2019, again, we contributed. In 2017, we were part of the NIST call for proposals. We were involved in 2 submissions. Those 2 submissions are still in the round 2, and there'll be 2 that I'll talk about in a little more detail. And we're active today on sort of 3 core draft standards in this space. 2 within the IETF on how to do hybrid key exchanges for TLS 1.2 and TLS 1.3, as well as the editor for a technical specification on how to do hybrid key exchange. So what is a chem, and what are the 2 submissions that we are involved with? So the first is a scheme called BIKE. It stands for a bit flipping key exchange. I have to admit they have maybe one of the cooler logos in the contest, or the NIST process. NIST is trying not to call it a contest. And SIKE, which is a super singular elliptic curve isogeny key exchange. So again, this is still using elliptic curve, but it's not using the same discrete log problem that Shor's algorithm applies to. So these are 2 post-quantum key encapsulation mechanisms. So I'm not going to go into the gory details of these other than to provide you sort of like an API specification of how they work. So if you've seen any crypto talks, Alice and Bob eventually always show up. And in this case, Alice is going to run the key generation algorithm that's going to generate an asymmetric key pair. And then she's just going to send the public key over to Bob. And in all my slides, I try to keep whatever's secret or doesn't leave the host in this dark orange. So hopefully I'm consistent. Bob will then run an algorithm called encapsulation. Encapsulation takes as input the public key, and it produces 2 things. It produces a shared secret and a ciphertext value, and sends that ciphertext value back over to Alice. Now Alice can run the decapsulation function, taking her private key, S sub k, and the received ciphertext to produce the same shared secret. So there's quite a large family. There's still 17 round 2 post-quantum public key encryption or key encapsulation mechanisms, and I've color-coded them. They basically span 3 sort of core technologies. One is something called lattice-based cryptography. Those are in orange. One is called code-based, of which BIKE was a code-based scheme. And finally, there's just one in the elliptic curve isogeny category, SIKE. So I've kind of put bullseyes around the ones that we're involved in. And across the bottom, I have sort of a logarithmic scale of the number of CPU cycles sort of that key encapsulation protocol takes for these various schemes. And along the y-axis, I'll call it quasi-logarithmic. I've just kind of spaced it out a little to make sure I have enough space to put all the schemes in. And down at the bottom, across sort of the bottom x-axis, you can see the schemes that we're used to using today. There's elliptic curve Diffie-Hellman, which is small, takes roughly 100 bytes to do that. The key exchange over the wire takes less than 1 million CPU cycles. For both parties to sort of do the computation. It's very efficient. And then we have RSA, which is still relatively small, 3072, that's in bits. But it's relatively expensive, and it's one of the reasons why we don't use it in an ephemeral key agreement scenario. And you can see SIKE is towards that end of I guess, the spectrum. And bike is somewhere in the middle. And so what I've done is, these are all from the NIST submissions when I look at the reference implementation. All right, so the reference implementation is not optimized. It's written for comprehension, to make it easy to understand what is going on. By and large, you get one sort of shift down, get to shift this down one sort of order of magnitude. So you would see psych drop down below 100 million. You would see bike drop down to close to where EC Diffie-Hellman is today. But they also have quite large, some of them, bandwidth requirements. And this doesn't really tell the full picture. So you have McLeese up and NTS Chem up at 300,000 bytes. That's going to change the way you write your protocol. That's not going to fit in a lot of packets, for instance. And it doesn't, as I said, doesn't tell the full story. Sometimes the public key and the ciphertext are roughly the same size. Sometimes the public key might be 100,000 bytes, and the ciphertext might be 32 bytes. So it's not, this doesn't tell the full story on how you might engineer with it. But the other thing, that was also all at the 128-bit security level. So I'm trying to make equal comparison on that slide. And again, I can do the same sort of weighing of how much analysis has been done. And quite a bit at the end of the day on all these schemes, or at least the core technology has been studied for quite a while. In fact, the code-based schemes, McLeese, predates RSA. So there's a relatively high confidence, although it's not very usable at 300,000 bytes, there's still relatively high confidence in the security of that scheme. Elliptic curve isogenies has been studied as part of elliptic curve crypto in general, using isogenies to attack classical elliptic curve crypto. But also it's been a field of study in mathematics for quite some time. And then lattice-based cryptography has certainly been around since before 2000, when the scheme NTRU first sort of was made public. So where are we? Well, we have a whole bunch of new algorithms that have a varying amount of assurances, both not just in their security, but also in their end implementation. What will a standard look like? It's going to change as we make advances, even between round 1 and round 2 of the submissions. These algorithms changed. We found optimizations to make them more efficient. So they're by no means sort of in a standardized format. But we still want to learn, how is this going to impact our applications today? Opportunistically, how can we get maybe some notion of quantum forward secrecy in our communication? And the answer is we can just do both. We can sort of do things in a hybrid key exchange model. So we can use one classical scheme like EC Diffie-Hellman and one post-quantum scheme like Bike or Psych, and combine them in a non-lossy way. So we call this hybrid key exchange, or hybrid key agreements. So what I have again on here is Alice and Bob, and this time they're doing sort of the classical elliptic curve key agreement. So Alice generates an asymmetric key pair, an elliptic curve key pair, and sends the public key A over to Bob. Bob generates an elliptic curve key pair and sends his public key B back to Alice. And then they can both compute this shared secret, taking their private key and doing the scalar point multiply of their public key, of the received public key, to get the same point on the curve and derive a shared secret that they can communicate with and secure their communication. So hybrid just sort of piggybacks on that process. It generates, Alice also generates a post-quantum key pair and sends that public key over to Bob. Bob runs the encapsulation function, gets a shared secret and a ciphertext value, and sends that ciphertext value back over to Alice. That allows Alice to run the decapsulation algorithm with her private key and the ciphertext to get the same shared secret. And then they can both run a key derivation function in a way that ensures that an adversary would have to know both the shared Diffie-Hellman secret A times B, as well as the post-quantum shared secret. HSS. So the next work is how do we put this into TLS and how do we implement it in S2N? So I'm assuming most people are familiar with TLS. It's probably one of the most widely used cryptographic protocols, certainly over the internet, encrypting TCP/IP traffic. All of HTTPS goes over this. It's designed to authenticate both endpoints, but in practice, we only really use it to authenticate the server. So the client gets to authenticate that the server is indeed who they say it is. And then they engage in an elliptic curve, typically an elliptic curve key agreement today, to get a shared secret. And then they can use that to protect their application data. And over there, sort of now you can authenticate the client. The vast majority of I think all our APIs come over a TLS protected channel. So quick sketch on TLS, at least this is TLS 1.2. Is we have a server like, let's say, S3, and has a certificate associated with it, as well as a private key. I've written that sort of in the RSA notation. So D and N is the public key, and E is the private key. And a client will connect with a client hello message. The server generates an elliptic curve key pair, puts the public key into the server key exchange message, and signs it with its private key, and sends back to the client their certificate and the signed server key exchange. The client can then validate that the certificate came from a certificate authority, was issued by a certificate authority that they trust, validate that they're really speaking to an S3 endpoint, can verify the signature on the server key exchange, verify that this is an authentic session with an S3 server, and then generate their key pair, elliptic curve key pair, and put that public key into the client key exchange message. And then both entities can sort of derive their session keys to encrypt the communication channel and put an S3 object securely into their bucket. And here I've dropped some of the other, there are a few other messages that go across, but I've dropped them because these are the only ones that really sort of matter for the purpose of building a hybrid key agreement scheme. The other messages stay roughly the same. So the next part was where do we start in modifying what library? We used to use OpenSSL's libSSL everywhere. We've replaced that. So today we use something called S2N, signal to noise. This is an open source implementation of TLS. And what we've done is removed a lot of sort of the CRUF, the backwards compatibility stuff that is built up in the OpenSSL, libSSL library. We no longer want that backwards compatibility, that added code complexity. So we were able to design it to be a little smaller, faster, with simplicity as a priority. Today it's available in AWS Labs, and it currently is handling all of the Amazon S3 traffic today. We've also been able to invest additional security in terms of partnering with our internal group, the automated reasoning group, to sort of write algorithm specifications in a language called Cryptol, run a software analysis workbench with an external company called Galois, who contributed to this project, and integrate those proofs into Travis continuous integration so that code is reproved every time there's a pull request on the library. And so we have some confidence that there are no memory errors in the original S2N, and that we have some input-output equivalence between the code and the specification. And in particular, there are proofs for HMAC, the hash-based message authentication, DRBG, which I probably should have spelt out, is a deterministic random bit generator that we use for generating random bits for securing that communication. And finally, the entire TLS handshake. So post-quantum S2N, I'll start again with, here is the TLS 1.2 as it was before, and we're going to just augment it with a post-quantum chem. So we can add in the server. The client hello is slightly modified to say I'm willing to do a hybrid scheme. The server can respond by generating an asymmetric post-quantum key for key encapsulation. and send that public key along in the signed server key exchange message. The client goes through the same verification, authenticity of the certificate, the server key exchange, and runs the encapsulation function or algorithm to get a shared secret, and sends that shared secret, the ciphertext, in the client key exchange message. And that allows the server to then run decapsulation and get the same shared secret. And both parties can now derive a new quantum-safe hybrid set of keys to secure their communication. So we've done this by first publishing a draft RFC within the Internet Engineering Task Force. So the IETF sort of defines basically all the standards we use today for Internet traffic: TLS, IPsec, SSH, DNS. And we've added Cyc and Byte to the reference implementation to the S2N code base, and we've implemented these two new cipher suites, namely EC Diffie-Hellman ephemeral with Byte and EC Diffie-Hellman ephemeral with Cyc. And we applied the same rigor to this new code base of S2N as we did originally to S2N. In particular, we used Byte 1, so Byte is really a family of algorithms. There's Byte 1, Byte 2, and Byte 3, and it comes in a few different security levels. We used Byte 1 level 1 and something called Cyc P503. That's a specific security level within the Cyc specification. And we did the same practice of putting this specification into Cryptol, running the same proofs to ensure that we have no memory leaks, that has equivalent I/O behavior between the specification and the code. And again, just like the original S2N work, this is all publicly available and built into the continuous integration and is in the open source repository. So what happens in practice? Well, the client hello gets a little bit larger. It's pretty moderate, just enough to send sort of an additional cipher suite and a client hello extension to say what version or what PQ scheme I want to do. So in particular, I'm going to do Byte 1, level 1, or Cyc P503, similar to how elliptic curve handshakes are negotiated using the client hello extensions. The server key exchange gets a little larger. For Byte, it adds 2,600 bytes. There's very little compression there. For Cyc, it's adding roughly 500 bytes, I guess, to the size of the server key exchange. For client key exchange, we're seeing the similar expansion. These two happen to be fairly symmetric between the ciphertext and the public key for the chem. And so you get a total handshake. You're looking at maybe about 800, 900 more for Cyc and roughly 5,000 more for Byte. But the story reverses itself when we start to look at CPU. I'll remind you that this was done with the reference implementation. We think we get an order of magnitude improvement here. So we've set up this hybrid server in one of our regions, US West 2. We did connections on the local host, a client in the same data, same region, a client in a neighboring region, a client in the London region, and a client in the Mumbai region. And you can see that you're getting, the latency sort of begins, I think that's a typo in the ping column over there for Mumbai. You're adding quite a bit. You're adding about roughly 25 milliseconds to the Byte code and about 150 milliseconds to the Cyc code. And we think that'll come down an order of magnitude when we get to assembly or optimized versions. The P99 is roughly the same. I guess that's not too unexpected. These are well-trodden sort of networks between our regions. There's not a lot of network diversity. We think as customers begin to use this over more diverse networks, we're going to see the P99 latency sort of have a different sort of distribution. The larger packets are going to start dominating, causing additional latency because networks won't as reliably transmit them. So what comes next? Well, first, we're going to increase the performance. We're going to move from reference code to optimized code. We'll add a lattice-based chem. I think as we depicted in the slide, there were 3 basic technologies: code-based, supersingular isogeny-based, and lattice-based. We'll add a lattice-based scheme into it. We'll move from the round 1 to round 2 candidates. This was done starting with the round 1 candidates. The round 2 candidates were made in January, and we're going to integrate, upgrade them to the round 2 candidates. So in time, we'll integrate PQS2N into our existing SDKs and deploy PQ hybrid into service endpoints so customers can have the real-world experience of doing their AWS call and understand how this tool will affect the applications that they're writing today. And then, of course, we'll move from 1.2 to 1.3. Moving to 1.2, 1.3, we're considering revisiting how we're thinking about hybrid key exchange. So if you go back to that thing that keeps me awake at night, it's a single point of failure that's keeping me up. It's not, and the single point of failure that I'm hyper-focused on today is quantum computing sort of being a threat. But tomorrow it'll be something else once I get that solved. It'll be the encryption algorithm, or it'll be the hash algorithm. And so I'm always going to be up at night. And so I have this notion of the double hull. So you've probably seen, like, the modern tankers have something like 7 or 8 holes inside them to prevent oil leakage. So the idea is you have a double hull connection. And so this allows us to keep a FIPS certified outer shell of what we're used to engineering with: EC Diffie-Hellman ephemeral, TLS with AES 256 and SHA-384, and put in the middle another set, another tunnel of completely orthogonal algorithms. So there's no overlap. So we get 2 independent family of algorithms. So an adversary would have to break both schemes in both of these to circumvent the security. So here you could do cha-cha, post-quantum chem, and a SHA-384. Of course, this adds session complexity. And that's something I think Amazon is always happy to try to pick up and control on behalf of the customer. You have twice the key derivation. That's a one-time setup call, and twice the encryption work. Most of the encryption engines that we use today can easily handle line rate encryption. So that's it. I have some additional topics that we're working on as they show up. As we hear from our customers, we're certainly interested in hearing from you. We did an earlier version of the hybrid into OpenSSH. That's available today in the Open Quantum Safe network, or Open Quantum Safe project called OpenSSH. We're looking at how do we do VPN technology. There's a bigger problem we see in VPN. A lot of people are using one of the default groups, which is a 1024-bit Diffie-Hellman, which again, as I said, is below sort of the normal security bar. And we're looking to sort of augment IPsec schemes to also do post-quantum key agreement. We've been pushing what we can do with the classical encryption schemes. We gave a talk this year on the derived key mode for KMS, how we were really stretching the lifespan of what we can reliably build high assurance systems with AES without doing something unique like this derived key mode or GCM with the synthetic IV. And what we kind of need here is some wide block ciphers that increase the assurances. It also increase the algorithm diversity that we can use to engineer our products. And finally, we're looking at new cryptographic models. So how do customers decrypt their data to be able to compute on it? And this is a real hard problem. We don't think we're going to solve it or solve it alone. But we're looking into how can we build privacy-preserving machine learning methods using this. So if you're interested in hearing more about the quantum safe stuff, the ETSI IQC Quantum Safe Cryptography Workshop is going to be held this year at Amazon headquarters in Seattle, November 5th and 7th. It's broken into 2 tracks, an executive track to help people understand what the issues are in terms of modifying their protocols and their infrastructure, as well as a technical track, sort of go through the state of the art and what's being done in the standards, as well as in the research community. It's still open for submissions if people want to make a submission. I have a slide with additional details. The most important is probably the AWS labs that you can download the post-quantum S2N today. It's in S2N mainline. You just have to enable, configure it to use these new hybrid key agreement schemes. So with that, I'd like to thank people who collaborated with me, mostly internal, a few external people, and thank you for coming after lunch. So thank you.